Hi, good evening, everyone. So, welcome to another TA section of our course, Data Science for Engineers. So, am I audible? Can someone verify that? Okay, fine. All right. So, I had to reschedule the meeting for today. Sorry for that. Tomorrow, I won't be able to attend the same. So, if anybody has any engagement at this time, the videos will be uploaded in the YouTube channel. You can also watch that. Right, so I will get on going with this class. All right, so we are discussing about data science and the mathematical side of that. So first, in the second week, we learned the linear algebra part, like how the data is represented, how matrices come into play, and how different techniques can be applied to those matrices, how the rank, nullity, everything is related, and all those things we discussed in the second week. And in the last week, we learned about probability and statistics. So in probability and statistics, mainly we um, saw how different distributions are there and how different distributions can be identified, or what are the terms in those distributions, like mean, variance, how they can be found out, the formulas relating that. Then we also discussed different um, aspects in axioms in probability, also different concepts in probability, like conditional probability, and all those things we discussed in the last week. And this week we will be discussing on optimization, and we will be restricting our discussion on unconstrained optimization for this week. So we'll mainly look at problems, because that can make you learn better. So again, welcome to the class. So if somebody has joined late, so we'll be discussing on optimization in today's lectures. So so what is optimization? Before moving on to the mathematical aspects, let's discuss optimization from a layman's point of view, or how it can be defined in our day-to-day life. So Wikipedia defines optimization like, so optimization problem consists of maximizing or minimizing, so it should be and metric, minimizing a real function by systematically choosing input value from within an allowed set and computing the value of the function. So what does it actually mean? So in our day-to-day life, we all try to optimize things, right? So whenever we have exams, we allot more time to study. So that is kind of an optimization. We are optimizing our time based on the requirements. Or whenever we need to plan something, we do optimization. So optimization is not something that we don't do. It's what we do naturally in our life. Okay, so here we have an example. So here we have three routes: route A, route B, and route C. So in this, example, as we can see, the route A is something very long route, right? Even though our aim is to reach the destination, that is to reach point Jalna from Pune. So we have three routes here. So route A is the longest route, and it takes like around 6 hours 70 minutes. And we have the another two routes, that is route B and route C, in which route B is the shortest in time. Okay, so if you look at the time taken to reach the destination, the route B is the shortest. That it takes only 6 hours 3 minutes. whereas root C is the shortest in distance. That is, it's only 289 kilometers. So optimization, we cannot say that in every optimization the requirement is the same. Even though our aim was to reach Jalna from Pune, but we have three different routes. And if someone wants to reach there in fastest time, he has to choose the route B. Or if someone is caring more about mileage, or he wants to travel less distance, then he has to choose route C. So optimization based on the constraints, we have different solutions. Now coming to mathematics, the optimization takes the form like it's kind of use of specific methods to determine the best solution to the problem. So it's like in this example, let's say, so here we have drawn one line. So we are talking about this example. So here we have a line. Okay, and yeah, so here we have one line. But as you can see, these distances are higher in this case. So if we had plot our line in a different way, so like this, it would have represented, or it would have minimized the losses. That is, these distances from the point to the line will be minimum if we change the line to here. So in mathematics, the optimal solution is represented for this problem by this green line. So optimization uses techniques to find this best solution. Now, this was the regression problem. Now coming to classification problem. So here we are asked to classify the data, the blue and red data. So with one training epoch, we got some line. So if you want to optimize this problem, we can plot or we can draw another line like this, so that the red area and green area, so the red area and there is no blue. Okay. So the blue area will be very well separated. So this finding this best lines or classify for this classification problem is an optimization problem in mathematical perspective. Now coming to the main topic for today's discussion, that is the univariate optimization problem. So what we will be discussing today about this univariate setting is that we have an objective function and a decision variable and constraints. So univariate in the sense it is a single variable. So here x is the only variable that decides the value of the cost function or the objective function. Okay. Now, as we have seen, we have three parts. One is the objective function. Here the objective function is the f of x. The decision variable is the x, and constraints are the constraints are something that we give in addition to this. So here one of the constraint is x belongs to real number. So the complex numbers will not be a part of the set. Or we can say x is greater than 5. This can be another constraint. Or let's say mod x is less than 5, so that the x can vary only from -5 to 5. So these are all constraints that we give to our function, because in many cases these decision variables cannot take whole real number space. Now coming to the solutions, So in here, we have restricted our x to be from, let's say, from 0 to 1.2. Now we want to find the solution. Now, if we had, let's say, if we had constrained our x from, let's say this is 0.7, so 0.7 to 1.2, then the minimum is here. So now the function is only this branch. So the minimum comes somewhere here. So this is the minimum. So such minimums are called as local minimum. So local minimum is the minimum within the interval. Now, if you take this entire set, so if you take the entire set, still this is a local minimum. So we have one local minimum here, then we have another local minimum here. But this local minimum is also global minimum, because in the entire set, we only have, or the this point is the lowest point. So compared to any other point, this is the lowest point. So if you want to write mathematically, so so if you write f of x is less than f x star, sorry, x star is less than f of x, then x star is local minimum if x star is, if x is in near neighborhood. That is, if we consider in all these x's, we had an x star, and x is near neighborhood of x star. So here it is an x star, and this whole is x. Whereas if it has to be this, so this is for local minima. Now if the point has to be a global minima, then f of x star has to be less than f of x for all x that belongs to the real number line or the specified domain. So that is the difference between global minima and local minima. Similarly, we have global maxima and local maxima. It's the same definition, but in a maximization point of view. Now, there are two conditions which needs to be satisfied for a point to be an optimal point. An optimal point can be, so optimal point, it can be minima or maxima or saddle point. So let's see. So this is our objective function f of x. Subject and our variable is x. And we have some constraints. Now the necessary condition for x to be a minimizer is f dash of x should be equal to 0. So if you look at the graph, so let's say, let's go back to our previous graph. So if you look at these points, don't look at these 2 points, the extremities, because there is one issue if you consider these two global maxima, and if you consider this one also, this is also a local maxima. So if you don't look at these 2 points, if you look at here and here, we can see that the line is parallel to the x-axis line. So as a in a graphical or in a graphical way, we can say that even if we change x, so what is let's say this is y, then dy by dx is nothing but y2 minus y1 divided by x2 minus x1. That is equal to f of x2 minus f of x1 divided by x2 minus x1. So remember this formula. Now we are coming here. So if you look at the optimal points, that is the maxima, minima points, let's say we are not considering any interval. So there is no open interval like we have considered here. So this line goes somewhere to infinity, and this line also goes somewhere to infinity. So this goes to minus infinity, this goes to plus infinity. So we don't have any boundaries. So if a point has to be an optimal point, then we know that the line is parallel to the decision variable axis. So we can say that the derivative of the function at those points will be equal to 0. Now here also we see the same condition. Here also it is parallel to the axis. So if you see here, this is a local maxima. So this is a minima. This is also a minima point. But what about this point? In this point, if you see, so in here, just one point is derivative is equal to 0. At one single location, the derivative is equal to 0. Whereas if we take this line, so let's try to enlarge it and see. So here we have a line whose value is constant, so that the f dash of x is equal to 0 in this entire line. So such points are called saddle point. So it's neither a minima nor a maxima, but those points are called saddle points. Now, how to identify these saddle points? So first, the necessary condition for the x to be a maxima or minima is, or a saddle point is, f dash of x has to be equal to 0. Now, if x has to be a minima point, then the second derivative has to be greater than 0. So for these 2 points, if you find some x, and if you find the second derivative of x and substitute this x here, the value has to be positive, so that it will be a minima point. Whereas if f double dash of x is less than 0, that is if it is a negative, then it will be maxima. Or if f double dash of x is equal to 0, or we cannot define it, then it is a saddle point. So these are the 3 conditions or 3 situations in the second sufficient conditions that we arise. But for checking the sufficient conditions, or to check if the point is a minima or maxima, this necessary condition has to be satisfied. So we will see one problem so that it will be more clear. So you guys can practice it, and yeah. So first you have to find the f dash of x, or the first derivative. Okay, so I will start. So f dash of x will be nothing but x cube minus 3x, so x square minus 2x. Now we equate this to 0. So if we take one x out, So we will be left with x square minus x minus 2 equal to 0. Further factorizing, we can write it as x minus 2 and x plus 1 equal to 0. So x is equal to 0, and then we have 2 or minus 1. So x is equal to 0, 2 or minus 1 satisfies this equation, the equation f dash of x equal to 0. And now we have to find if which point is the minima point. So like we have already discussed, we need to find f double dash of x. So that is equal to 3x square minus 2x minus 2. Now we have to substitute each of these values into the equation. First, let's substitute, or first let's find f dash of 0. So that will be equal to minus 2. Then we find f double dash of 2. So that will be equal to 3 into 4 minus 4 minus 2. So how much it will be? 3 into 4, 12 minus 6. So it will be equal to 6. Then we have f double dash of minus 1. So that will be equal to 3 into 1 minus 2 into minus 1 minus 2. So that will be equal to 3. So in here, we have two values, that is 2 and minus 1 satisfies our condition f double dash of x is greater than 0. So both of these points are minima points. Now let us see which is the actual minima. So for that, or global minima. So these two are local minima points. So we have to find the um, global minima among this. So first we will find f of f dash of 2, no, f of 2. So f of 2 will be something, let's say 2 raised to 4 by 4 minus 2 raised to 3 by 3 minus 2 square. So if I calculate that, 1 minute, let me calculate. So if you somebody have calculated, you can please read out the value. Okay, so that will be equal to minus 2.67. Then we have f of minus 1. So that will be equal to 1 by 4 minus plus 1 by 3 minus 1. So that will be equal to 1 by 4 plus 1 by 3 minus 1. 3 minus 1. So that is coming to be negative 0.41. So here we got that f of 2 has the lowest value. So the minima of this function exists at x equal to 2, and the value is minus 2.67. Whereas this is a maxima value. Okay, so the solution is here. I will upload this slide. So we have another question. So somebody please try to answer this. Yeah, somebody has a raised hand. Sudhakar.
Sorry, sir. Yeah, myself,
Yeah,
sir.
yeah, tell
How
me.
did you obtain that F dash, sir? I'm sorry, I might have missed the previous classes.
F
How do you
dash.
obtain the F dash of X?
No, f dash of x, it's like it's just factorization. So let's see. So what we have here. So we have our f of x, right? So let's say we have our f of x equal to x raised to 4 by 4 minus x cubed by 3 minus x square. Now what we
Yes,
are
sir.
trying to find is dou by d by dx of f of x. So we are taking the derivative. So if you are taking derivative, the x raised to 4 will be using the formula. So x raised to n is n x raised to n minus 1. D by dx of x raised to n is n x raised to n minus 1. Now if you use that, we'll have 4x raised to 3 by 4. This one will cut off. Then we have 3x square by 3. This 2 will cut off and 2x.
Yes, sir. Yes, sir. Thank you, sir. Right, sir.
Okay. Then we will do the factorization and we equate to
Yeah.
0 and find the
Actually, I forgot it.
x.
F dash is d by dx of x. Yes, sir. Thank you.
Minus 2.67 is global minima, sir.
Yes. Yes, exactly.
Okay, sir.
So
Global
if you
minima will be greater than the local minima, sir.
no, global minima will be less than local minimum.
Okay, sir. Okay, sir. Thank you, sir.
It's minus 2.6, right? So it's less than.
Okay, sir.
Here's
Okay,
the
sir.
okay. Since it is minus, it is less than this thing. It is less than minus 0.4. Okay, so now please try to answer these two questions.
Sir, option B.
Option A.
Option A is not correct. We are talking about local minima. So
Right, sir.
yeah, option B is the correct. So option, and for the second one, just do f dash x and we can find it. So if you do the f dash x, it will be 2x minus 4. Now equating that to 0, what will be the x?
Option C, sir.
So option C. So let's say x is 2. So x is equal to 2. Now f of x is equal to 4 minus
Sir,
8
option
plus
A.
5. Okay, yeah, option A is the correct answer. And here option B is the correct answer. Okay, so now one more question. So of all the rectangles of area 100, so which has the smallest perimeter? So here is a question where we have a constraint also. So first you try to formulate the function or the objective function, and then it will be easy to solve. So let's begin. So I'll start it. So we have the area. Area we can write it as length into breadth of a rectangle. Then perimeter we can write as 2 into L plus 2 into breadth. Now it is given area is equal to 100. So we can write 100 is equal to L into B. So now here the constraint comes in the form of this 100. So the area is restricted so that there is some control or some relation between length and breadth. Now we have to find the optimal solution, that is the smallest perimeter. So this is the perimeter function. So let this be the function perimeter. Now try to convert this function perimeter, that is 2L plus B, 2L plus 2B, into a single variate problem. We have not considered the double multivariate problem till now. So try to convert this this equation into single variable, that is either to L or B. So for this, you can use this equation. So if you convert length or breadth is equal to 100 by L. So from this equation, we can write breadth is equal to 100 divided by L. Now we put this back into our objective function. So we can write 2L plus 2 into 100 by L. Now our function perimeter is just a single variate function of L. So we can write, so earlier this was a function of length and breadth. Now it is just a function of length. So let's try to find the f dash of L. So f dash of L is 2 minus 200 by L square. That is dou by dou x of 1 by x is equal to minus 1 by x square. So from that we write this. Now equate this to 0. So we can write it as, so from this we get 2L square is equal to 200, or L square is equal to 100, or L is equal to plus or minus 10. So whenever we take the square root, both plus 10 as well as minus 10 can come. But since in this question we are dealing with length, breadth, or area, so minus 10 is not a possible solution because length of a rectangle cannot be negative. So in such problems, we have one more constraint, natural constraint, that is length breadth is greater than 0. So now we have the length is equal to 10, and we can again use this formula. So from here we get breadth is equal to 100 by 10, which is also equal to 10. Now the smallest perimeter we can find, that is P is equal to, perimeter is equal to 2 into 10, 2 into length plus 2 into breadth. That will be equal to 40. So in here, the difficulty is in formulating the objective function. So we have to formulate the objective function and find the solution. Okay. So let's move on. So it's a straightforward question. You can just calculate. So it will be little difficult to calculate. You can use the calculator and do it. So we'll just look at the solution. So here the problem, the cost function is 0.0001 q square minus 0.08 q plus 65 plus 5000 divided by q. So this is the objective function that we have to minimize. So just so this is a single variate function in q, where q is the number of units, daily average of producing a certain product. Then if you take the first derivative, we end up with this equation. On solving that, we get q is equal to 500. Now, if we take the second derivative and substitute this q in the equation, we will get a positive value. So here this term is positive and this term is positive and q is also positive. So anyway, this is going to be greater than 0. Now, so that essentially give the solution of the problem. That is, the number of units to be produced is 500 units. So again, a similar problem what we have done just now. So now here the constraint is on the perimeter, not the area. So yeah, can you quickly do it so that so we'll look at the solutions, or if you are trying, I will wait, or we'll look at the solutions.
Option B.
Option B, question number 1. No, it's not the correct answer. Can you check again? Somewhere you have done some miscalculations.
Sir, for that critical point question, option is D. X is equal to 1, X is equal to 3. Option
Yeah,
D is the right answer.
Yeah, it's correct. And for question number 1,
I am trying, sir.
option 1 is, yeah, option 1 is the correct answer. Okay, so you can try, and here we have the solutions. So here the perimeter we have constraint to be 24. So again, we'll use the area equation to maximize. So here the area equation we'll substitute, instead of length or breadth we can substitute, and once we solve this equation we will get breadth is equal to 6 and length is equal to 6. Okay, so yeah, again so this is also straightforward. You have to just take the derivative and tell the answer.
Sir, option B, sir, X is equal to 10.
Yeah, fine. And for the second,
Option D, 11 milli per second. Option
11,
D.
yeah, fine. So in this case, you don't have to take in a derivative. It's asked what will be the velocity at 2 seconds. So you have to just substitute 2 into this equation and find the answer. No, actually this is speed, so you have to take the derivative. So derivative will give the velocity. Sorry for the confusion. Okay, so yeah, let's move on. And now let us see multivariate optimization. So until now we have seen a single variable is changing, and we were finding the objective function with respect to that single variable. Now we will be dealing with multivariables. So in this case, let's say z is a function which is defined as x1 square plus x2 square. So by varying both x1 square and x2 square, we can get different contours. So here, if you see here, if x1 is equal to 0 and x2 is equal to 0, the cost function f of x is also equal to 0. Whereas if we increase both, so let's say we are taking -5, so that will be too much or what? So if you're taking somewhere here, the point will be somewhere on this whole circle will have the same value, so that the function value will be somewhere higher. So here we use the contour plots. So if you look from above, so if you look somewhere from above, we'll see something like this. That is, here we have the 0 value. Then depending on the increasing value of x1 and x2, we'll see the value of z is increasing in the radial direction. So this is for the case of only two variables. Now, if you have multiple variables, so it will be hard to imagine. So let's say up to three variable, we can easily show it. So if we had a three variable function, simple function, so let's say we had function x1 square plus x2 square plus x3 square. So we'll have something kind of a ball, so a sphere or something which is centered at the 0. So the small ball will have some radius, then a bigger ball will have a bigger radius. So it will have, so if all the x1, x2 and x3 are equal, we'll have a regular sphere, or else we'll have some, so if some of the variable is higher or some of the variable is lower, we'll have some structures like elongated spheres or oval shape in a 3D way. So that is a multivariate optimization. So yeah, these are for single variate itself. So a minima or maximum of f of x exists if it satisfies the necessary condition, that is f dash of x is equal to 0. Then maxima exist when f double dash is less than 0. So I think this slide came later, sorry. Okay, so this is one of the one case of that multivariate thing. So here we can see, here there are a lot of let's say peaks and valleys. So here we have a lot of red points here, and we have kind of so here we have a lot of blue areas also. So all these are some way or other the local minimas, and all these peaks are local maximas. And at the middle, let's imagine at the exact center, that is here, we will find the global minima for this particular case. Whereas all these blue areas, so all these blue areas all these blue areas are local minimas, and we have the local maximas in this yellow or red dots. So these kind of problems are kind of difficult to solve. So mostly in optimization, we will be stuck in some local minima. So if we had started from somewhere here, our search, we might have ended up here. Or else if we have started somewhere near to the global minima, we might have ended up in our global minima solution. So that is in many optimization techniques, we have to be careful where we start the optimization procedure. So in the multivariate case also, we have the conditions that has to be met in order to find the saddle point or the minima point or the maximum point. So the necessary condition, just like we had for the single variate case, which was for single variate was f dash of x has to be equal to 0. So for multivariate, since a lot of variables are there, we will find the gradient by something called as Jacobian. So this is called Jacobian matrix. So Jacobian matrix is nothing but it will give the derivative of each and every function in a matrix form of the function with respect to each and every variable in a matrix form. So here we have the derivative with respect to x1, x2 up to xn. Now, if we find this matrix and then we will equate that to 0, we'll find the so how we can find in the sense like we'll have so here we have n number of variables. So we need n number of equations. So if you find the Jacobian, we'll find a matrix which has 1, 2 up to n. So here belongs to dou f by dou x1 up to dou f by dou n xn. So we'll have n equations and n variables. So we can find exact solutions using the methods that we have discussed in the linear algebra class. So this is where we can connect the linear algebra to the optimization to find the optimal solution in case of multivariate optimization. Now we have the necessary condition which has to be met. That is, we have to equate this to 0 and find all the variables. And the sufficient condition is the positive the matrix has to be positive definite. That is, the matrix or the second derivative, which is called the Hessian matrix, should have positive eigenvalues. So let's say, so the so once we find this one, so once we find the Jacobian matrix, now what we do is we take the derivative of, so let's say we have dou f by dou x1. We take the derivative of this one with respect to all the other variables. So we have dou f by del square f by del dou x1 square. Then we have del square f by dou x2 dou x1. Then we have del square f up to dou x1 dou xn. And similarly, now we have to find all the rows. So we will have n columns and n rows. N rows we already have here. So it is an n cross n square matrix. Hessian is an n cross n square matrix. And also one more thing, we can say that all these elements will be equal to these elements. So it is a symmetric matrix also. So del square f by dou x1 dou x2 will be equal to del square f by dou x2 dou x1. So we are using dou in the sense that these are partial derivatives. So let's say what is partial derivative? So let's say we have a functions like f is equal to x1 square plus 2x1 x2 plus 3x2 square. So this is the function that we are trying to solve. Now let's find out what will be the Hessian and Jacobian of this matrix. Okay, so let's find that. So the Jacobian will be, so we have to find dou f by dou x1 and dou f by dou x2, since it is having two variables x1 and x2. So this will be, so the partial derivative of f with respect to x1 will be 2x1 plus 2x1 2x2 plus 0. So while calculating the partial derivative, the other variable, so when we calculate the partial derivative of f with respect to x1, we'll be considering only x1 as a variable, whereas x2 will be considered as a constant. So if you take the derivative of ax square with respect to dou by dou x, so it will be 2ax. Whereas if you consider dou ay with respect to x, it will be 0, because here both a and y will be considered as constants. So now dou f by dou x2, so it will have 0 here, then we will have 2x1 plus 6x2. So now we have the what we call the Jacobian matrix. Now let's find the Hessian also for this matrix. So Hessian will be del square. So it will be del square f of x. So that will be, so we have to, first we have to take the derivative of this. So we have to take the derivative of this one with respect to both x1 and x2. So if you do that, we will get 2, sorry. So if you take first with respect to x1, so we will get 2. Again, with respect to x2 also, we will get the 2. Now we are taking the derivative of this one with respect to x1. So it is 2 again. And if you take it with respect to x2, it is 6. So if you look at this matrix also, you can see this is a symmetric matrix. So this one is equal to this this number. So only the diagonals will change, whereas this lower part and the upper part will be exactly similar to each other or symmetric to each other. So even if you find this part of the matrix along with the diagonals, the rest of the part we can fill. So that is about about calculating the Hessian and Jacobian matrix in case of multivariate optimization. Okay. I will write the function, 1 minute. So the function is two variable function. It is x1 plus 2x2 plus 4x1 square minus x1 x2 plus 2x2 square. So this is the function. So you can just tell me the final in the Hessian matrix. So first you have to find the Jacobian and try to solve for x1 and x2. Then if you can, just try to give me the last answer of the Hessian matrix. Okay, I will in 2 or 3 minutes you can give me the answer.
Sir, del square x is 8 minus 1 minus 1, 4.
Yeah, that is correct. Okay, so
Yeah.
so I think there is no confusion in finding the Hessian and um, Jacobian. Okay, so if you find the Jacobian also, so Jacobian matrix will be nothing.
Jacobian del square
Yeah,
F is Hessian, no, sir?
yeah, del square F is Hessian. So Jacobian is 1 plus 8x1 minus x2, then 2 minus x1 plus 4x2. Right?
Sir, then gradient and Jacobian are same, sir.
Yeah, gradient and Jacobian are same.
Okay, sir. Okay, sir.
So now we have to equate this into 0, 0. So then if we solve for x1 and x2, we'll get some value like we have to calculate it. So if you calculate, you are going to end up with 0.19 and 0.54. Okay, anyway, these values are not required to calculate the Jacobian since there is no. So if we had some square terms in here, so if you had any square terms in the Jacobian, some x1 or x2 will be in the Jacobian and the Hessian also. So you will need these values to be substituted in the Hessian to find the final value. So now what you have to do is you have to find the eigenvalues of this Hessian matrix. So the eigenvalues of this Hessian matrix are, it will be 3.76 and 8.23. So both are greater than 0. So this is a positive definite matrix since all the eigenvalues are greater than 0. So we can say that there is a minima at the at these x1 and x2, or at these critical points we have a minima. All right. So let's see some theoretical questions. So in multivariate optimization, what is the critical point of a function?
Sir, option B at the point where the function has a local minimum, the critical point of a function.
A point where the function has a local minimum. We are asking only about critical point. Critical point can be minima, maxima, or saddle point.
Option D, linear function is linear.
What we have just seen right now. So what is the condition? So again, so this is the necessary condition, right?
Mhm.
So now try to read the options again.
Option C. Option C.
Yeah, option C. And for the second question, in multivariate optimization, what is the role of Hessian matrix? So don't think in sense of multivariate. Go back to univariate and think what did the second derivative did.
Finding the critical points.
Now, critical points we found from the first derivative, that is the gradient.
C option. It's providing information about the functions.
So actually it is providing the information about the curvature. Okay, so yeah. Another question. So calculate the gradients of f of x equal to 4x square minus 3xy plus 6y square at point 0 and so x is equal to 0, y equal to 1.
Said option A.
Yeah. Option A is the correct answer. And the second one, so you will have to take derivative twice.
Option B.
Yeah. So just from this first values, you can get the answer, right? So if you do del square f by dou x square, you get 8. So from that itself, you can finalize the answer. All right. So again, we have some more questions. So just substitute x and y into the equation. So what will end up? So 4 plus 4, it will be equal to 8.
Option 8.
And for the second one, we'll have to find the eigenvalues. So yeah, try to do that. So the Hessian matrix, or the del square f, will be what? It will be 6 minus 2, then again minus 2, then 4. So this is the Hessian matrix. Now what we need to do is we need to find the eigenvalues. So let's find that. So we have 6 minus lambda minus 2 minus 2, 4 minus lambda. Then we take the determinant, 6 minus lambda into 4 minus lambda minus 4. So what we get, lambda square minus 10 lambda plus 20. Now we have to find the values. So let's say lambda is equal to minus b plus or minus root of b square minus 4ac by 2a. So if you substitute the values, we get 10 plus or minus root of b square is 100 minus 4 into minus 4 into 20. So it will be, so it's not 100 square, 100 minus 80 by 2a. 2a is 2. So we will end up with 10 plus or minus root of 20 by 2. That will be equal to 5 plus or minus, so 20 we can write it as 2 root 5. So we will end up with 5 plus or minus root 5. So these are the two eigenvalues. So if you look at both the eigenvalues, so one is 5 plus root 5, that is greater than 0. Also 5 minus root 5 is also greater than 0. So since both the eigenvalues are greater than 0, we can say that the Hessian is a positive.
Local minimum.
Definite, yeah. So it's a local minimum.
Sir, in the above problem, we just want to substitute the values alone. In the previous problem, that x square plus 4y square, we just want to substitute the point alone, sir. The 2 should be substituted in the x, and the minus 1 should be substituted in the, for that alone,
Right.
or we have to take the derivative, sir?
No. So already the critical point is given. So if you try to find the critical point also, we will get, we can find the critical points. Then what we need to do is we have to, so it's said that a critical point is 2 minus 1. Maybe it is, or maybe it is not. So if you look at this equation, maybe it is some extreme points, but because if you find in our natural way, so it will be 2x and it will be 8y, the Jacobian. So
Yes,
our
sir.
solution is
Sir.
x is equal to 0, y is equal to 0. So this is not what they have asked. So what they have asked is there is some critical point at 2 minus 1. So what is the value of the function at this critical point? So maybe
So just we have to substitute in the x we have to substitute 2 and in the y we have to substitute -1. That alone is enough, sir.
yeah, that alone is enough.
Okay, sir.
Okay, so now try to answer this one also. Then we will move on to the next topic.
Sir, the last option, sir. 2 is local minima, 3 is local maximum, 1 is the saddle point.
2 is local minima.
1 is the saddle point, sir.
Yeah, that is correct. So we have two options now, this one and this one.
Last option, sir.
So 3 is local maxima.
Yeah.
Mhm. So what about what if I say if this is an infinite space? So let's say let's not restrict the boundary. So in what I think what you have thought it. So these points are local minima, right? And these points are
Yes, sir.
local maxima. So if we extend this space to beyond that, so this can represent local minima here also, right? So we have, and this will be local maxima, local or global maxima. One thing to note is that all global maximas are local maxima. All global points are also local points, whereas all local points are not global points. So that
Yes, sir.
is one condition that we have to see. So both can be both A, B, C. So this is D, right? Both C and D can be right, depending on how we define the problem. Okay, and the last thing, so last question, and this one, which option will be correct? So in here only one option is correct. So if you look at the curvature, here is the curvature coming the flat or coming parallel to both the x1 and x2 axis. So if you keep a plane here, so that plane will be parallel to the x1 and x2 plane. So if you think in that sense, which one will be the correct option? Anyway, for saddle point, we know it has to be equal to 0. So these two, from these two, we have to select one of the option. So if you look at the second plot, this is a local maxima and this is a local minima. And so now we can say that this one will have positive definite matrix. So f double dash of x should be greater than 0. And in this case, if it is a local maxima, the Hessian should be less than 0. Although the matrix will have negative eigenvalues. So that option 2 will be or the figure 2 represents f double dash of x less than 0. All right, and so now we will move on to unconstrained optimization problem, that is directional search. Okay, so if you look at the function space as shown here, we will have the global minima here, then we have the global maxima. Also, we have some local minimas and local maximas. So it's like kind of a landscape with the hills and valleys. So if our objective is to find the minima point, so if our objective is to find the minima point, we need to reach the global minimum. Or so let's say we start from somewhere here. So this is the global minima that we have. But whereas we have some other, so this one also can be a minima. So we start from here. So we move in a fashion like where the function is decreasing the value. And finally, we can reach the global minima. So our aim is to reach the bottom point in the search. But there can be times that we reach the local minimum. So in optimization, it depends on where we start our search. So let's say we start our search somewhere here. So we start our search somewhere here. Then once we move, so if we took this direction and move, so we might reach here. So once we reach a local minima, then if you try to move up, we'll see that the function is increasing its value. So what we will think, or the algorithm will think, that we have reached a minima without knowing there is another minima which is present here. So there are different algorithms which will help us to reach the global maxima also. So it is so by looking at the direction, we will reach either we may stuck in local minima or we might reach the global minima. So the one of the techniques that is used is gradient descent method. So in gradient descent method, we will just like we move in this valley. From the starting point, we will find the direction of the descent, that is the steepest descent. And sometimes we will take further steps so that we will reach somewhere higher point than what is intended. And then we will again move down so that we can reach the global minimum. So let's see what is gradient descent method. So it is applicable to find the minima of the given function, and it is one of the techniques that is applied to a back propagation algorithm to find the network parameters in the neural network. So how we find it is like, so we start from some point. So let's say this is xk. So this is the first point that we start. Now in order to find xk plus 1, we will add xk, we'll add this term to xk. So what is this term? So alpha is the step length and sk is the direction. So in this problem, so let's say we had taken a step length of this much. So then we'll so from starting here, we found this direction and we had taken a step length long enough to reach this point, so that we will reach exactly the local minimum. Whereas in another attempt, what we did is, instead of taking this long step, we took, instead of taking this one simple step, we took some long step. So we reached somewhere here. Or let me try to explain it. So first, let us say we took this step. So we reached here. And if we take the derivative now, the direction will show to be moving into here. So that we will, in 2 steps, we are going to reach somewhere in the local minimum. Whereas in another attempt, we took long step so that in the same direction, we took a long step so that we will go here and we'll reach here. Now, if you take another step, or we'll find the derivative and the direction, we will find that this is the direction to move so that we will reach the global minimum. So that the step length plays an important role in gradient descent method. So alpha is the step length and S denotes the direction to move. So first we will start from some starting point and then we move towards the optimal solution. Okay, so step 2 is a search direction, that is the steepest descent direction. So whenever we take the derivative of the function or the gradient of the function, so let's see, so we had seen this contour, right? So it was increasing the function value in this direction. So if you take the derivative of the function, it will always point towards this direction. But we have to find the minima. So we have to move in the opposite direction. That is, we have to move in this direction. So this is the green is the direction that we have to move. So that direction is nothing but the negative of the derivative. So the negative of the gradient of f of x is our direction to move, or the search direction. And the new point will be updated based on the step length. So let's see how the step length can affect. So here are 2 examples. An example where we start from the same point. So this is our function x square plus 4x plus 1. So we have the function defined by the blue line. And initial, we have learning rate of 0.1. And in another case, we are taking a learning rate of 0.8. Okay. Now, first, if we calculate the direction, calculate the derivative, it's 2x minus 4. So our direction to move is xk minus step length into the descent direction. So if you use the small step length, so in the first attempt we will reach somewhere here. Then if we move, we will reach somewhere here. So yeah. So first in the first step we will reach somewhere to the 1 point, then 2, then 3, and so on. Since the step direction is smaller, we will reach our solution slowly. Whereas in this case, in the next case, so if you see after first step, we will reach somewhere here. So that is equal to 7.6. In the second step, we reach around 6.48. Then third step, we reach 5.84. Whereas in the next step, we are taking longer steps. So once we take longer steps, we can see this kind of oscillations. So in the first step itself, we changed our direction to somewhere here. So that is minus 2.2. Then in the next, we will move to 4.52. And so let's see. So this is 4.52. Then again, we moved back to the other side of the solution. So that is 0.48 and so on. So we can see that the step length plays an important role. And there are complications also which can come because of the wrong choice of the step size. So here are some other examples where we can see in how many iterations or in how many steps we need to do the optimization to reach the solution. So if the step size, also called as learning rate, so learning rate is nothing but the step size. So the learning rate or the step size, if it is small, we will need more number of, so it's just like walking, right? So if you're walking in with small steps, we need a lot of steps to reach our destination. Whereas if you are having longer steps, we'll reach our destination faster. But if you are jumping here and there, you'll reach finally, but it will take a lot of effort. So that is what we are seeing with this example. So if the learning rate is very less, we'll reach the final solution, but in a very slow manner. So here we took 24 iterations, whereas when we increased our learning rate to 0.3, we reached our solution in 8 iterations. Again, if we increased, then we see that the iterations increased to 15, then to 33 on increasing the learning rate to 0.9. So, so here we see a lot of oscillations. Here we see less oscillations. Here we don't see oscillations and faster convergence also. So this is what the implication of changing learning rates can have due to the optimization. So here is another example or another animation which shows different gradient methods, gradient descent methods or optimization techniques. So here again, if the learning rate is small, we finally reached our solution with a higher number of steps. On increasing, it reached again the solution in lesser number of steps. But whereas when we increased our learning rate to much higher value, actually the solution is deviating. So even though we wanted to reach our final solution, but the solution is kind of deviating from wherever we have started. So we will have a diverging solution in such cases. Whereas in this case, in the right figure, what we are seeing is we have started our balls exactly from the same position, but here we have a local minima here, and we have a global. So this is global, global, and local. So we have different optimization techniques like RMS prop, then Adam W, etc. So if you take an entire course in optimization, you will learn about all these things. So here, some optimization techniques, it will take smaller steps and reach here, whereas other optimization techniques like the blue, green, and white, they are moving much faster, and so you see the blue reaches first and followed by the green, and white is taking longer steps. So what we can say that is that the optimization technique that is followed by the blue is much better, even though white, green, and blue reached the same point in the end, but the optimization technique that was used by the blue is better. So we have different optimization techniques that is applied so that the our final goal to reach the global minima is attained. So all those are not in scope of this course to study. So just to understand this or the concept of the optimization, I have included this figure. So here this is a kind of a lengthier question, but it will be good to practice. So if you give some time and do it, please, we can find the solution x1 and x2 after 3 iterations. So what all you need to do, you need to find the gradient. So you need to find the gradient of the solution. Then so the step size is also given. So first the starting point is also given. So I will do the first step, then you can do the second and third step, and finally tell me the answer. So the first step is to find the gradient. So gradient of f will be 2x1 minus 2x2 plus 2. Then with respect to x2, it will be minus 2x1 plus 4x2. Now the first point is x1. So let's say x0 is 0, 0. So our equation is x0 minus alpha naught into S naught. So let's say take it as plus. So S naught is nothing but minus delta F. Okay, at X naught, F at X naught. So we'll substitute that. So 0, 0. Now minus 0.5 into, we have to substitute 0 to both x1 and x2. So it will be 2 here, then 0 here. Negative we have already given here. Okay, so finally the answer will be minus 1 and 0. So this is the x1. Now you have to find x2 from x1, not x0. So x1 plus alpha 1. Alpha 1 is same as alpha naught, so it's 0.5. But you have to substitute different values in S1. So it will be based on this x1. So it will be based on the x1 values. Okay, so you can do those 2 steps, please. By 7:30, you can give me the answer. So if somebody has answer, can share it. All right, I'll do it. So it is -1, 0, minus 0.5 into. So now we have to substitute -1 and 0 into our equations. So it will be 2 into -1 minus 2 into 0 plus 2. So it will be -2 plus 2, it will be 0. And then we have -2 into x1, that is -2 into -1 plus 4 into 0. So that will be equal to 2. So we will get -1 and -1. Now this third point, or after third step, it will be, we'll start from -1, -1, then 0.5 again.
-2, 0,
-2, comma
0.
0. Okay, so what will be here? It will be -2 plus 2 to 2, right? And in the down, it will be -2 into -1, that will be -2, -2, -4, it will be -6. So how is it 0? -1 -1 plus 3 it will be, so it will be
Yes, please.
how much it will be? Somebody -1 plus 3. So it will be 2, right? I'm doing something wrong.
Oh, -2, sir, this one.
-2, and what will be here?
2 minus
The
2. S3 values, S2 values.
x2 is plus 2.
S2, sir, S2.
Oh, sorry. This is, oh, sorry. -2 into -1 is 2, right? So, okay, sorry. This is 2 minus 4, that is -2.
-2, yes.
Yeah, sorry. So it will be 0, yeah. Yeah, that's correct. All right, so let's see some questions.
For the first question, option is A, and for the second question, the option is scalar value. Gradient is a scalar value.
What is the gradient? Why is
Scalar
gradient
value.
How is it a scalar value? It is giving us a direction where to move, right? See, a gradient.
Option C,
So,
sir. Option C. Vector pointing in the direction of a steepest descent.
B.
B is the correct answer. C, we have already said that. Where was that? Okay, negative of the gradient is the direction of the descent. So the gradient always points towards the ascent of the function, that is the higher values. So this is the direction of the gradient. All right, so the option B is the correct answer. Vector pointing in the direction of steepest ascent. That is what the gradient denotes. The negative of is, if I have asked the negative of the gradient, then option C is the correct answer. All right, so again, 2 quick questions.
Sir, algorithm converges quickly.
Learning rate is too small, that is step is too small. So if you take small steps, will you reach quickly in your destination or
Slowly.
slowly? Okay, then the second one.
Sir, learning rate, option B, lower learning rate increases the risk of overshooting.
Again, you are confusing. So we have seen already, right, in this. So see, whenever the learning rate is higher, we see these oscillations. So if the learning rate is lower, we don't see the oscillations. We see slower convergence towards the optimum solution. So whenever the learning rate is higher, we see the oscillations. So a higher learning rate can cause algorithm to take larger steps, which can increase the risk of overshooting or the minimum, and it can cause the oscillations. Okay. The explanation is given, so you can answer the question number 2. We have not discussed stochastic gradient descent also, so try to answer this question.
The stochastic gradient, option B, sir. Memory is required.
No, actually the answer is C. So anyway, we have not discussed about stochastic gradient also. So don't stochastic gradient means like we are random updates. So we will be starting from random points. So the problem is when we start from random points. So if you start from somewhere the local minima. So if we have some global minima here, then if we have some local minima. So in the stochastic gradient, we can start from any point. So it's the point where we start is stochastic. We are not using any deterministic approach to find the starting point. So if you start here instead of here, so if you are started from here, we will reach the global. Whereas if you had started from here, we will reach a local minimum. So there is chance if we start from some random point to reach the local minimum. The second question.
Sir, option B.
G is the gradient. G is the
Option
gradient.
D, sir. Option D. X nu is equal to X plus G by A. Fourth option.
How? We have already discussed the point. Xk is equal to xk plus 1 is equal to xk plus alpha
Plus
into
alpha
S.
into S.
So alpha was the learning rate or step length, right?
Sir,
So here
option B, then second option.
B is also not the correct answer because here this was the gradient direction S and not gradient direction, the steepest descent direction. But steepest descent direction is nothing but negative of the gradient. And here it is given the gradient. So if you substitute minus G, the option A will be the correct answer.
Okay, sir. Okay.
Okay. So you don't have confused between the steepest descent direction and gradient direction. So gradient direction is always points towards the higher values, and steepest direction is negative of the gradient. Okay. All right. So the last set of questions, and yeah. So what will be the answer? So if you multiply 0,
So is it option A?
yeah, option A is the correct answer because we have to take the negative one. Okay, so and again, if the initial parameter value is 8 and the gradient step length is 0.2, what is the updated parameter value?
Option
But
B,
not
8.2.
yeah. Okay, so I will share these slides and shall we discuss some more problems since we have 10 minutes left? Okay. So we'll quickly go through the questions. So there are like 20 more questions. So no theory, so you can quickly answer. So we have two correct options in this. So these stationary points are -2 plus 5 or -2 minus 5. And if you find the second gradient, we'll see that this option is the minimum of f of x. And yeah, the function is given. So take the derivative twice. So we will
For the
reach
previous sum, can you just explain the steps, sir?
this
For the, can you
this
just work
question.
out the step for, yeah.
Okay, so first we take the derivative. So it will be f dash of x is equal to 3x square plus 12x minus 3. Okay. Now this is a quadratic equation. So to find x, we can use the formula minus b plus or minus root of b square minus 4ac by 2a. So minus b is minus 12 plus or minus b square is 12 square. That will be 144 minus 4 into a into c. So since we have negative here, so 144 plus 4 into 9, 36 divided by 2a. So that will be 6. So we'll get minus 2 plus or minus root of 144 plus 36 will be 180. So from 180, if you take the root, how much it will come? 180 is nothing but 36 into 5 is 180. So if you take root, so it will be 6 root 5. So we get 6 root 5 by 6. That will be minus 2 plus or minus root 5. So we got it. So we got stationary points minus 2 plus 5, minus 2 minus 5. Now what we can do is we need to find the second derivative. Sorry. So if you find the second derivative, we will end up with 6x double dash is equal to 6x plus 12. Now if you substitute both the points here, so first point is 6 into minus 2 plus 6 into root 5 plus 12. So since root 5 is greater than minus 2, so root 5 is something greater than minus 2, right? So, root 5 is greater than 2 itself. So we can take 6 into root 5 minus 2. This will be positive, and f double dash of x will be positive. So since f double dash of x is positive, we can say that this point is a minima point for f of x. Now if we use the other point, so that will be minus 2 minus root 5 into 6 plus 12. So this will be the f double dash x. Anyway, that option is also not here. Anyway, we will see. So if you look at this option, so we have minus 2 minus 5. So minus 5, root of minus 5 is greater than root of 4. So an approximation, we can say 6 into minus 2 plus 12. So it will be 6 into 4, that will be 24. So minus 24 plus 12, so it will be minus 12, so which is less than 0. So the point minus 2 minus root 5 is a maxima point. Okay. So the next question, we have to take the derivative twice. If you take the derivative twice, we get 4 into 3 is 12x square plus 7 into 3 into 2, that will be 42x plus 10. Now this has to be, so x has to be maxima. If we x has to be a maxima here, it has to be less than 0. And find the value of x star. So that is a lot of calculation. You can do it. So this is the correct option, and we have the answer here. Now the next question. So in this case, we have constraints, that is 0 and 2 pi also we have to consider whenever we are calculating. So first we have to take the derivative, then this 2 cos x equal to 0. So dash of x So cos x will be what? Cos x will be 0 when x is equal to pi by 2 or 3 pi by 2. And we have to see the second derivative, that is minus 2 sin x. And if we put pi by 2 here, so we know that pi by 2 sin pi by 2 is equal to 1. So the f double dash of x will be negative. So it is a global minimizer. Now it's a global maximum. So pi by 2 is a global maximum. And also if we substitute the next point, that is 3 pi by 2. So 3 pi by 2 sin 3 pi by 2 is minus 1. So minus of minus 1 into minus 2 will give plus 2. So it is greater than 0. So it's a global minimum. So we have another question. So this is straightforward. We have already done a lot of things. So just the derivative, if we find, we get the answer. Then if we equate both the equations to 0 and solve it, we find the stationary point and find the Hessian and find the, then we have to find the eigenvalues. So if you find the eigenvalues, we find that both are positive. So it's a local minimum or the minima point. Now for this one, again, we have to say follow the same steps, but here we have multiple options. So first you have to find the stationary point, and to see we have, if we have an, the EC matrix is positive definite or not positive definite, that we can find by finding the eigenvalues. So you can practice these questions. Then in optimization problem, the function that we want to optimize is called the objective function.
Objective function, sir.
What?
Objective function.
Yeah, objective function is the correct answer. Okay, then in optimization, minimum of f of x can also be written as maximum of f of x.
False.
Is it true or false? Yeah, it's false. So minimum of f of x is equal to minus maximum of f of x. So if this was given, it is true. Okay, so this statement is false. Okay. So in a gradient descent algorithm, the step size should always be same for each iteration.
False.
Yeah, it's
Sorry,
false.
sir. True.
No, this is false
false.
actually. Okay, actually the case is, so one idea or one algorithm that we choose is, so if you see, if you have taken, if you were to take small steps from the beginning, we will reach our final solution very slowly. So what you, or if you take only big steps, then there is a chance that these steps will go here, go here, go here. Then it will, if this is the minimum, it will oscillate between these 2 points without reaching the minimum point. So what usually in the algorithms, we set it like this. First, we will take bigger steps so that we'll reach somewhere near. Then we take small steps so that we will reach our solution faster. So it is not necessary that at each step the learning rate or step size has to be the same. That's why in the equation also, so if you write xk plus 1 is equal to xk plus alpha k sk. So we write this as alpha k. So at each step, this k can be, so in the first step, we can take a higher value. In the next step, we can take a smaller value. Then we can reduce. By each step, we can reduce the value so that finally we will reach the optimal solution. Now, so this is just taking the gradient. So we find the answer. Then again, if you find a solution to the gradient, we will find the answer for this question. Then find the second derivative. That is find the sufficient condition and check for the minima or maxima condition. Okay, so this one is also kind of same question. All right, so there are not a lot of variety questions. So a class of optimization problems with no constraints are known as
Option B.
unconstrained optimization. Then the optimum of a function exists if
Positive option B.
how come?
No, second derivative should be positive. F of x, f dash of x is equal to 0. Option A.
Yes, correct answer. Okay, then one more.
So the region of inequality constraint will be greater. Option B.
Yeah, B is the correct answer. And yeah, this one needs some calculation, so we won't just take the first order derivative and we find the answer. So this question, the restriction on the possible values of R, the values of the solution.
Sir, equality bar inequality constraints.
Okay, yeah, that's it. All right, so thank you for joining today. So I will upload the material as well as the video. You can go through that. All right. Yeah. If you have any doubt, we can discuss, or else I will close the meeting. Okay, so thank you for joining. Okay. All right. So if you don't have any, doubt, I will just end the meeting.